All right, so I'll talk about machine learning for mechanism design, and in particular about sample complexity guarantees for data-driven mechanism design for revenue maximization for multi-item, multi-buyer scenario. Okay, and let me start by putting this work in a bit of a broader context. So what do I mean by data-driven mechanism design? I mean the use of machine learning to design and analyze mechanisms based on data. Okay, and as you might know, this is actually an increasingly popular area of algorithmic game theory. The idea itself was proposed a couple of decades ago, before machine learning was widely popular. And several papers that propose these ideas include a paper that I had with Ishai Mansour, with Avrin Bloom, and with Jason Harline in Fox 2005. We had a paper on this topic. It was actually called Mechanism Design via Machine Learning. There's also related work there are also related ideas proposed in the AI community, for example, by Thomas Handom and Anton Lihododov. So these ideas were proposed a couple of decades ago, but in recent years there has been a surge of interest in trying to use machine learning techniques for mechanism design. Okay, and this interest is actually very natural. Why? Because there are several scenarios, including some of the scenarios that I'm going to talk about today, where at least currently it's hopeless to characterize analytically the optimal mechanism or the approximately optimal mechanism. And so it's very natural to try to use machine learning and data in order to at least compete with the best mechanism from a fixed restrictive family of mechanisms. Okay, so it's a very natural idea. In my talk today, in particular, what I'll tell you about is about statistical or sample complexity guarantees for this data-driven mechanism design approach for revenue maximization. So I'll focus on revenue maximization and multi-item, multi-buyer scenarios. And what I'm going to present is mostly based on this paper joined with Ellen, who is right here in the room, and Thomas Handom. So this is an EC18 paper. And the main result here, the main result of this paper was really kind of a crisp, unified, I think elegant sample complexity analysis for several data-driven mechanism design classes. Okay, and of course, and actually, the technical ideas that I'm going to talk about, I mean, I really think should be of interest beyond this specific case, revenue maximization scenarios that we analyzed. And in fact, I'll mention this at the end of my talk. They should be of interest, I mean, beyond actually mechanism design. So similar ideas can be also applied, for example, for data-driven algorithm design, so much more generally. Okay, and I'll end the talk with some more general comments about it. Of course, there are many other connections between machine learning and mechanism design, and you'll see one more later in the day. So Ellen will tell us about using machine learning theory for analyzing a related mechanism design problem. Okay, so you'll see another connection there. All right, so with this introduction, so I'm going to focus for the rest of the talk on this specific sample complexity result from this EC18 paper, and it was for revenue maximization for multi-item, multi-buyer scenarios. So we'll be thinking about mechanism design for sales settings. So here we have a set of M items. We assume that we have a set of M items, and we have also N buyers. And we also assume that each buyer, of course, each buyer I will have a value for each bundle B. And I'm going to denote by VI, so this is a vector of, for buyer I, the vector of all valuations for all bundles or for all subsets of the items.
It's an annoying shade here.
Okay.
Go on.
All right. So for buyer I, I'll denote by VI the vector of valuations for all subsets of the ground set. Okay, and at a high level, we know that the mechanism determines which buyer receives which items and what they pay. And in particular, a mechanism is defined by an allocation function and by a payment function. And the allocation function defines which buyers receive which items, and the payment function defines how much each buyer pays. And when given a mechanism M, I'm going to for a given mechanism M, given the valuation vectors V1, V2, Vn, then the revenue of that mechanism is just the sum of the payments, which I'm going to denote this way. Okay, and so just a couple of examples of mechanisms to think about when I present the general framework. One first example is that of posted price mechanism. So we assume that the buyers arrive in an arbitrary order, and what we do, we set a price. So we're trying to sell multiple items. We're going to assume that the buyers arrive in a fixed but arbitrary order, and what we do, we set a price per item, and then, oops, this is going too fast for me. So Isha, can I actually use your, because I'm more used with your clicker. I keep going back and forth. Sorry, I apologize. It's the same, but it's too sensitive for me, and I keep going back and forth. Thank you. Okay. Right. So a quick example of a mechanism is a posted price posted price mechanism. So here we assume that the buyers arrive in a fixed but arbitrary order. We're going to set a price per item, and then each buyer comes in order and will buy. Each buyer buys what the buyers want at the current prices. So we're going to buy the bundle that maximizes its utility function, which is the value minus the price. Okay, so that's one example. As another example of a mechanism that we'll consider in this work is second price auctions or reserve prices. So here we just have one item for sale, and first the auctioneer sets a reserve price R, and then bidders submit bids, and then the highest bidder wins if its bid is at least R, and pays the maximum between the second highest bid and the reserve price R. Okay, and so, for example, in this quick example here, if the reserve price we set is 8, then the revenue we get is 8. Why? Because the highest bidder wins and pays 8 in this case, the maximum between the second highest bid and the reserve price. On the other hand, if the reserve price in this example is 6, then the revenue we get is 7, because this is the maximum between the reserve price and the second highest bid. Okay, so these are just quick examples of mechanisms that we might be considering. Now let me describe how we can think about mechanism design for these settings as a machine learning problem. Okay, and here I'm going to use kind of a distributional learning formalization, and I'm going to build on statistical learning theory techniques. Okay, and if you are familiar with machine learning, this is like supernatural formalization. Okay, so what we're going to do, we first fix a problem that we want to solve. And this can be an auction problem, a pricing problem. And then what we do, we also fix a large family of mechanisms for this problem. Okay, and we're going to denote this family of mechanisms as calligraphic M. Okay, and this can be a family of mechanisms that either is commonly used in practice for that problem, or we somehow have analytical reasons to believe it might be good for our type of kind of data. Okay, and then what we do, we take a set of samples of the buyer's values which specify their values for all subsets of the items, and then we use this set of typical samples in order to come up with a mechanism that we hope does well on the underlying distribution, right? So we're going to assume that this set of typical samples of buyer values for various subsets of the items are drawn IID from a fixed, potentially unknown distribution over buyer's values for various subsets of the items. And the goal is to use this set of typical samples to come up with a mechanism from this family of mechanisms, calligraphic M, that we want to have high expected revenue on new random valuation vectors coming from the same distribution as a training set. Okay, so to go a bit more slowly, so we fix a problem that we want to solve. This can be an auction problem or a pricing problem. Then we fix a family of mechanisms for the given problem at hand. So for example, if we are trying to just auction one item, we might be considering the family of second price auctions or reserve prices. Okay, or if we are trying to price multiple items for sales, we might be considering the family of posted price mechanisms, right? And note that this family of mechanisms, calligraphic M, is actually infinite, because in both of these examples, we have some real valued parameters that we can try to tune, like the reserve price for the second price auctions, second price auction or reserve prices, or the prices, right, for the posted price mechanisms. Okay, so we fix the problem that we want to solve with this large family, parameterized family of mechanisms, infinite parameterized family of mechanisms, and then we take a sample of buyer's values for various subsets of the items, but we assume that are drawn IID from a fixed unknown distribution over buyer's values for all subsets of the items. Right, so for example, for the second price auctions, the reserve prices are only trying to sell one item, right? Now, how the samples look like? Well, each sample, because we only have one item, each sample will just list the values of each buyer for the given item, right? So this is sample number 1 here, the value of the first buyer for the given item, the value of the second buyer for the given item, and so on, the value of the nth buyer for the given item. This is the first sample, and we have capital and such samples. Okay, or for item pricing, we are trying to price multiple items for sale, right? Now, each sample will list the values of each buyer for all subsets of the items, right? So, yes?
How do you sample distribution?
Yeah, what does it mean? So, it's a good question. So, one instantiation, you might have historical data. Okay, so that's one answer. Another answer, like sometimes, I guess in mechanism design and economics, you assume that you know somehow the distribution, right? And you are still trying to design a mechanism with respect to that distribution.
Those are known distributions.
Yeah, but this formalism will work for known or unknown. I was just saying, I said potentially unknown distribution. Yeah? So it's in a way even stronger. Now, of course, there are questions. Do you really have this information from historical data? That's the second question, but let's assume that you have. So either the distribution is known and you actually sample yourself, or it's unknown, but somehow you magically assume that you have these samples in this form. Yeah? Right. So, so for posted price mechanisms, this is how our samples will look like. We'll list the values of all of our, so in each sample, we're going to list the value of all our n buyers for all subsets of the items, and have capital and such samples. Okay, and based on such samples, IID samples from this distribution D, which could be is fixed, but could be either unknown or known. What we want to do, we want to come up with a mechanism from the family of mechanisms calligraphic M that has high expected revenue. And in particular, what we want to do, we want to compete with the best mechanism from this family of mechanism calligraphic M with respect to this fixed distribution. Okay, and we want to do so based on these samples. Okay, so that's basically a statistical learning or distributional learning formalization of mechanism design as a machine learning problem. And the most natural thing you can do here is, in order to solve this problem, it's what we always do in machine learning, but also the most natural thing you can do. How are you going to solve the problem? You're going to find a mechanism M hat from your family of mechanisms, calligraphic M, that is either optimal or nearly optimal on the given set of samples, right at hand. That's the only thing you can do. Right? And so that makes a lot of sense, but of course the key question here is whether this mechanism M hat will also do well on new random valuation vectors coming from the distribution, the same distribution as the training set. Right? So in other words, will you generalize? Will you have high expected revenue on new samples coming from the same distribution? Right? So for example, for the second price auction reserve prices, the mechanism M hat that we find based on the training set of typical samples, of course we're going to do well on the training set of typical samples because we've chosen it so. But the key question is whether this mechanism M hat will also do well on new random valuation vectors that we have not seen in the training set. Okay, and of course the answer to this question will depend on how many training samples we've seen in the training phase, right? Because if we've seen very, very few, there is really no hope to generalize. But as we start seeing more and more such training samples, we can hope to generalize. And so basically a key question here is what we call a sample complexity question, which is how many training instances, how many typical instances do we need to see in the training set in order to guarantee that the mechanism that does well over the training set of typical instances will also do well on new instances that we've not seen in the training set. And again, by doing well, really, I mean I want to compete with the best mechanism from this family of mechanism calligraphic M with respect to the unknown distribution. Okay, this is what I mean by doing well. Okay, now the answer to this question, so this is a sample complexity question, and of course we can build on tools from statistical learning theory to understand this question. And there are various tools that one can try to use. You can use uniform convergence bounds, you can use covering number bounds. What we use in our work is uniform convergence bounds. And what are these uniform convergence bounds? They are, roughly speaking, bounds on the number of samples we need to see in the training phase in order to guarantee that uniformly, that with high probability over the draw of the training sample, we have it uniformly for all mechanisms in our family of mechanisms calligraphic M where empirical performance or the average performance, average revenue over the training set of typical instances is close, say additively close to where expected revenue with respect to points coming from the same underlying distribution. Okay, so these are uniform convergence bounds, and the cool fact about these uniform convergence bounds is that, of course, once you have uniform convergence, if you have enough training samples to have uniform convergence, then this immediately implies that the mechanism M hat that does all over the training set of typical instances will have high expected revenue. So in particular, its revenue will be very close to the revenue of the best mechanism from this class of mechanism with respect to the underlying distribution. Okay, so once we get uniform convergence, we get generalization. Okay, so that's great. And another nice thing is that we know from learning theory, at a high level, roughly speaking, we know exactly how many training samples we need in order to achieve uniform convergence. And in particular, we know that the number of training samples we need to achieve uniform convergence depends somehow on how intrinsically complex this class of mechanisms M hat is. And there are various notions of dimensions that kind of quantify this intrinsic complexity. There are notions like Rademacher complexity or pseudo-dimension. And at a very, very high level speaking, they quantify, in case you've never seen them, at a very, very high level speaking, they quantify kind of the ability of the revenue functions corresponding to mechanisms in this class to kind of fit complex patterns. And again, why? Because at a very, very high level speaking, the more complex the patterns you can fit, the more samples you need not to overfit, or the more samples you need to generalize. Okay, and so the cool fact is that basically we can now build on tools from learning theory to kind of understand the sample complexity question. And so what we'll know is that all you need to do in order to understand the sample complexity question for mechanism design, all you need to do is to understand these notions of dimensions for our families of mechanisms. Because once we understand these notions of dimensions, then we immediately get sample complexity bounds of the form that I have here on this slide, that will tell us how many samples we need to generalize. Okay? And of course, what's fun from a machine learning point of view is that actually understanding these notions of dimensions is also interesting technically from a learning theory point of view, because the structures that we get in this mechanism design context turn out to be very different from classic machine learning structures. Okay? So that's the high-level story. Like in this specific work with Ellen and Thomas that I'm going to talk about next, so what we did, we came up with a general way to analyze these notions of dimensions, in particular the pseudo-dimension, for a very large family of mechanisms whose revenue functions satisfy like a nice structure. Like it will be a piecewise linear function. Okay? And then we showed many applications. So this is actually a very slick, elegant theorem, very easy to prove once you have the right level of abstraction. And the nice fact is it has many applications to many mechanism classes. Okay, and this is what I'm going to try to do next. I'm going to try to describe how we compute these notions of dimensions for, first of all, what the general theorem is, and how I'm going to compute these notions of dimensions for several interesting mechanism classes. All right, so this is the high-level story. Any questions at this point? Because now I'm going to become a tiny bit more technical on the learning theory side. So any questions? Okay, there are no questions. I can move on. And so how many of you have seen VC dimension, actually? Okay, so the vast majority. That's awesome. Okay, good. That means I can go quickly. Perfect. So, what's VC dimension? So, well, this is a notion of dimension that characterizes the learnability or the sample complexity of classes of functions that are binary valued functions. Okay, so for example, linear separators. Okay, in RD. Okay, and so what's technically the VC dimension is the cardinality. The VC dimension of a class of binary valued functions is the cardinality of the largest set S of points that can be labeled in all possible ways with functions from the class. Okay, and actually when we can label a set S in all possible ways with functions from that class, we say that the set S is actually shattered. That's the terminology, right? And again, the VC dimension of a function class H is just the cardinality of the largest set S that can be shattered or labeled in all possible ways with functions from the class. So for example, if we're thinking about linear separators in R2, you can easily show that the VC dimension of linear separator here is 3. Why? Because you can show that there exists a set of 3 points, like 3 points like this in a triangle, that can be labeled in all possible ways with linear separators. But on the other hand, no set of 4 points, you can prove that no set of 4 points can be labeled in all possible ways with linear separators. Okay? And in general, the VC dimension of linear separators in RD is actually should be here d plus 1. Okay. And I'm not going to go, because I am, of course, I need to talk about our mechanism results. I'm not going to have time to go into details of why VC dimension is a relevant notion of dimension, but just for the couple of people here in the audience that have never seen VC dimension, just want to mention why would VC dimension be relevant at all for generalizability. Well, like, why does it matter how many points can you label in all possible ways with functions from the class? Well, because just some very fuzzy, very high-level intuition. Well, if we have a very, very complex class of functions, so for example, the class of functions of all 0-1 functions over some domain, then any set of points can be labeled in all possible ways of functions from the class, and the VC dimension of the corresponding class here will be infinite, which is good because, you know, of course, you cannot generalize over such a very complex class of functions. Why? Because given any training set of examples, that means points of labels, there will always exist two functions in the, like the blue function here and the, I guess the red function here, that perfectly label the training set in the same way, but have completely opposite behavior on any test points. Okay, and so we cannot hope to generalize, and this is reflected by the fact that this class of functions has infinite VC dimension. This is just very, very high-level intuition. Of course, the highly non-trivial and exciting thing is here requires a cool proof is that actually if the VC dimension is finite, then you can generalize. Okay, but this is for classes of functions that are binary valued, but when you think about mechanism design, revenue functions for mechanisms, for cell mechanisms, the corresponding functions are actually real valued functions. And so now we need to talk about the, a measure of complexity for real valued functions. And the one that we use in our work is what we call, it's the pseudo-dimension, which is really just the most natural analog of VC dimension to real valued functions. Okay, so what's the pseudo-dimension of a class of functions that are now real valued functions? Well, it's just the cardinality of the largest set of points that can be now shattered in a real valued sense. Okay, and what do I mean by being shattered in a real valued sense? I mean that the pseudo-dimension of the function class f here is just the cardinality of the largest set of points x1, x2, xn, but also with thresholds y1, y2, yn, such that all 2 to the n kind of above and below patterns with respect to these thresholds on these points x1, x2, xn are achieved with functions from the, our function class f. Okay, just to give a quick example, like if n is 2, if the size here is 2, then there should exist a function f1 in my class that achieves the below-below pattern, meaning f1 of x1 is strictly smaller than y1, f1 of x2 is strictly smaller than y2. So this is the below-below pattern, but there should also exist a function f2 that achieves the above-below pattern. So that means f2 of x1 is strictly greater than y1, and f2 of x2 is smaller than y2. But then I also need the below-above pattern and also the above-above pattern, right? So this is what I mean by real value shattering. Okay, and actually, if you think about it, actually, really, this is, there is an alternative intuitive definition. So this is a notion that I'm going to use in the proof, like this real value shattering, but really, if you think about it, what the pseudo-dimension of the function class, of a function class f is just the VC dimension of a related class of functions that are binary functions. So in particular, the pseudo-dimension of a function class f is just the VC dimension of the below the graph indicator functions, right? And where for every function f in my function class, original function class, I have the function below the graph, where in addition to the original feature vector x, I also had the feature for y, for the value of the function, and I just defined the below the graph function f for the below the graph function for the function f on the point xy is basically just 1 if the point xy is below the graph of the function f and is 0 otherwise. So it's basically the pseudo-dimension of a function class f is just the VC dimension of very natural related binary class of functions. Well, the most natural thing you can do. Okay, now the interesting fact is that now we have uniform convergence sample complexity guarantees as a function of the pseudo-dimension of a function class f. And roughly speaking, what these uniform convergence guarantees do, they are bounds, they are high probability bounds on where the probability is over the draw of the training sample that quantify, that uniformly quantify for all functions in the class. So, right, what we have here is that we have probability over the draw the training sample. We have it uniformly for all the functions in the function class f. We can bound the deviation of the empirical average of the function from the expected value of the function, and we can bound this deviation. We can upper bound it by using the pseudo-dimension of the function class f. We bound it by using a term that involves the pseudo-dimension of the function class f. So that the deviation is upper bound by square root of the pseudo-dimension of the function class f over n. So it decays the number of training samples, but the other key quantity here is the pseudo-dimension of the function class f. All right, so that's a quick tour, a quick introduction to uniform convergence bounds from learning theory. And so the key point here is all you need to do is in order to get these uniform convergence bounds, you need to analyze the notion of pseudo-dimension for our function classes. So now let me show you how we can analyze the pseudo-dimension of the second price auctions with reserve prices, and which then motivates the particularly simple proof that then motivates a more general theorem statement that will apply to many more function classes, to many more mechanism classes. Okay, so so recall in the second price auctions with a reserve price, we have one item for sale, we have in a single item multi-bidder scenario, and here the auctioneer first sets a reserve price R, and then the bidders submit bids, and then the highest bidder wins, and if its bid is at least R, and pays a maximum between the second highest bid and the reserve price R. Okay, so basically notice that here this mechanism class is parameterized by one parameter, the reserve price. So, right, and so this is one that we can tune based on samples. And so for this simple class of mechanisms, we can show that the pseudo-dimension is constant. Okay, and to show this, the pseudo-dimension of this family of second price auctions with reserve prices is constant. The key the key insight in our proof, the key insight is the following: it's a structure result about the revenue function. So here's the structure result. It says that if I fix a set of bids, which basically means just if I fix one sample, which just means a set of bids, right? So, and then if I vary the reserve price, then the revenue function is a piecewise linear function of the reserve price. Okay, so that's the key fact here. And it's very easy to prove. So let me fix a set of bids for the given item. And let's assume just pictorially that maybe the second highest bid falls right here, and the highest bid falls right here, right? And now let's imagine varying the reserve price, and let's plot the revenue function. Okay, when the reserve price is smaller than the second highest bid, then the highest bid wins and pays the second highest bid. Right? So that's why I get here this constant piece. Now, when the reserve price is in between the second highest bid and the highest bid, then again, the highest bidder wins and pays the reserve price. So that's why I get the linear function here, this piece here. And when the reserve price is bigger than the highest bid, then nobody gets anything, and nobody pays anything, so then the revenue is 0. Okay, so basically if I fix a set of bids and vary the reserve price, what I get is that the revenue function is a piecewise linear function with 3 pieces. Okay, but this is for a fixed set of bids for one sample, and to understand the pseudo-dimension or the intrinsic complexity of the family of mechanisms, I need to think about the behavior of these mechanisms on many samples, right? And so, but the key point is that we can immediately do so using this basic claim, and we can actually prove that the pseudo-dimension of the family of mechanisms which are reserve prices, second price auctions with reserve prices, one reserve price, we can prove that the pseudo-dimension is actually constant, is in fact at most 2. And how do we prove it? All we do, we're going to use the structure result from the previous slide. Okay, and here is the proof. So I'm going to go through the details of the proof here because it's simple enough. So, so I want to prove that the pseudo-dimension of this family of mechanisms is at most 2. So now let's fix just one sample. So that means a set of bids for the given item. And let me also, because I'm going to think about real value shattering, I'm also going to fix. So I'm also going to fix a revenue threshold YI, right? And so what I know So first of all, if I fix a sample VI and if I vary the reserve price, I know from the previous slide that the revenue function is this blue piecewise linear function, right? And now let me also fix a revenue threshold YI. And now let's notice that as we scan the reserve price from 0 to infinity, there will be at most 2 cutoff values, this critical value here and this critical value here, where the revenue goes from below, so this is the revenue, goes from below the reserve price to above from below below the revenue threshold YI to above the revenue threshold YI, and again to below the revenue threshold YI. Right? So if I fix one sample and the revenue threshold YI, as I scan the reserve price from 0 to infinity, there are almost 2 critical values where the revenue goes from below the threshold YI to above the threshold YI to below the threshold YI. Okay, but this is for one sample, and again, to understand the pseudo-dimension, I need to think about the behavior on many samples. But now if I have n samples, then I'll have 2 times n cutoff values. And now the key point is that for all reserve price, all reserve price in the same interval between 2 consecutive cutoff values, we're going to give the same above-below patterns. And so that means that I only have at most 2 times n plus 1 patterns that I can achieve as I vary the reserve price on the given n samples. Okay? On any given n samples. I can achieve only at most 2 times n plus 1 patterns by varying the mechanisms in my mechanism class. But if you recall, the pseudo-dimension of a function of a mechanism class n is the cardinality of the largest number of samples for which I can achieve an exponential number of patterns. And so that means in order to compute the pseudo-dimension, I need to compute the cardinality of the largest n, for which on one hand I can achieve an exponential number of patterns, but on the other hand it's hyperbounded by 2 times n plus 1. So I need to solve this little inequality, and then this shows that the pseudo-dimension here is at most 2. Okay? Yeah, so it's a great question. So actually this result, this is just a simple warm-up example for me to tell you, and actually to tell you a more general result. So actually this result, great question, thank you, because I was about to forget. So actually this result has been proven before by several people. It's been proven actually by Mehriar Mori and Andres Modena using Rademacher complexity calculus. It's also been proven by Jamie, but much more complicated proofs. And so this is just a 3-slide proof that actually 3 bullets proof, 1 slide proof that exploits the structure of these revenue functions. And what's cool about it is that it inspires a more general kind of proof strategy that applies to many more mechanisms. Yeah, so the result has been proven before, but here the novelty is a much simpler proof that is much more generalizable. Okay, and here is a generalization, so that's exactly what I'm going to do next. I'm going to show how we can generalize this idea to more general mechanisms. So now we'll be thinking not only about one item, not only about mechanisms for one item for sale, but we might have many items for sales. And now we're going to thinking about mechanism classes that are parameterized not only by one real value, but by many parameters, by say D parameters. So kind of the parameter vectors now live in RD. Okay, so we're going to assume that the mechanisms are parameterized by vectors that live in RD. And we're also going to assume that if I fix a set of Bayer's values, and if I vary the underlying parameter vectors, the revenue function is piecewise linear, where the pieces are given by most T hyperplanes. Right? So for example, for the previous example, it was a piecewise linear function with 3 pieces given by 2 kind of hyperplanes here. And so, but in general, now my mechanisms be parameterized by vectors that live in RD. And this is the first condition. The second condition is that if I fix a set of Bayer's values and vary the underlying parameter vector, I can partition the parameter space with a most hyperplane such that within each cell of the partition, the revenue function is linear. Okay, that's what I'm going to assume. And so then we are able to show that for such family of mechanisms, the pseudo-dimension is upper bounded by d log dt. Or D is again the dimension of the parameter space, the parameter vector, and T is the number of hyperplanes that define the partition. Right? So previously I had D was 1 and T was 2, but in general we can have higher dimensions, like in this example 2, and here T would be say 5. Okay? And so, and by the way, we call this family of mechanisms, we call them DT delineable. And so, and again, if they are DT delineable, we can show that the pseudo-dimension is D log dt. And so actually I would claim that this bound is really good. Why? Because it's only linear in D, where D is the dimension of the parameter vectors. And it's only logarithmic in T, the number of hyperplanes that kind of define the structure of the revenue function. Okay, and how many more minutes do I have? Because I want to make sure I time well. 10 minutes? 15?
So we should have started at 9, I guess, we started 9:15, so.
You can ask the chair.
Well, I can start negotiating. 18, oh, perfect. Fine, okay. Because I have 18 minutes, I have time to go.
No, I wasn't sure if it's supposed to be 45 or.
Okay, thank you. Okay, that's perfect. Okay, so the right number of minutes for me to give you a few details here. So, right, so actually, I'm not going to go through lots and lots of details here, but I want to actually give the high-level structure of the proof. So actually, this is a very general result. And it turns out that, again, the proof is not very complicated. And so once you have the right level of abstraction. So what we want to show is that if these mechanisms are dt delineable, the pseudo-dimension is of the order d log dt, where, again, d is the dimension of the parameter space, and t is the number of hyperplanes that define the partition, right? The number of hyperplanes that kind of that define the partition for each of the revenue functions. Okay, and how do you prove this? Well, the proof, now it's of course more involved and it uses more general tools from learning theory, but it really follows the structure of the second price auctions or reserve price. If I have one sample, if I fix a set of bidders' values and vary the parameters, I have a mostly hyperplane that partition the parameter space such that within each cell of the partition, the revenue is linear. But now if I have n samples, right, which is what I need to think about when I think about the pseudo-dimension, I'm going to have at most n times t hyperplanes. Right? And what I want to do is to kind of bound the number of above-below patterns I can achieve on these n samples. And how do I bound them? The very first observation is that if I have n samples, I have at most n times t hyperplanes that partition the parameter space that are relevant. Now, if I have at most, if I have n times t hyperplanes in RD, it's a result that you can prove in many ways, but for example, using Sauer's lemma from learning theory, you can show that if I have n times t hyperplanes in RD, they partition RD in at most m times t plus 1 to the power of d regions. This could be a consequence of something called Sauer's lemma. And now, in each region, we know, because it's in the assumption, in each region we know that the revenue function is linear, so that means that in each region we have m plus 1 to the power of d sign patterns, kind of above-below patterns. And so that means that overall, the number of sign patterns that we can get is, well, we have in total n times t plus 1 to the power of the regions, and within each region we have at most n plus 1 to the power of the sign patterns. So that means that the total number of sign patterns we can achieve is n times t to the, plus 1 to the power of d times n plus 1 to the power of d. This is the number of sign patterns, above-below sign patterns we can achieve on n samples. But recall that the pseudo-dimension of a function class is the cardinality of the largest set for which we can achieve exponential number of patterns. So all I have to do is to solve for the largest n, for which on one hand I have exponential number of patterns, but on the other hand, the number of patterns is smaller than this upper bound, but I know it's a strict upper bound on the number of patterns I can achieve with mechanisms from a class that satisfy my property. Right? So all I have to do is to again solve for inequality of this from 2 to the n is upper bounded by n times t plus 1 to the power of d times n plus 1 to the power of d, solve for n, and when I solve for n, I get that the pseudo-dimension is upper bounded by d log dt. Okay? That's a sketch of the proof. And this is very general, and by the way, it applies, it doesn't have to be a mechanism for, like the class of function, it's just the class of real value functions. It could be the class of revenue functions given by some mechanism, the context of mechanism design context, but of course it could apply to other class of functions. For example, actually in our work it also applies to algorithms for aligning sequences, for example, will have the same structure. Okay, cool. And actually one thing that I want to, and I'm going to show you some examples, but before showing you some examples, one thing that I want to highlight from a machine learning theory point of view, actually the proof is also novel. And why, and here's kind of the cool novelty at a high level speaking, like what's different here when we do this pseudo-dimension computation proof. Well, so here's the interesting fact. What we want to do, we want to prove uniform convergence for mechanisms parameterized by a parameter vector P, where P lives in RD, and takes as input valuation vectors, right? And we want to prove uniform convergence for such mechanisms, right? And so the way we do it, we are trying to basically compute the pseudo-dimension of mechanisms that are parameterized by parameter vectors P and take as input valuation vectors V. Okay, but to do so, what we really used in the proof that I showed you, both for second price auctions and reserve and the more general proof that I showed you, what we really exploit is the structure of what I call the dual functions. Right, and now the function in the dual now is parameterized by evaluation vector V and takes as input parameters vector P, right? Because in my theorem statement, I'm assuming that if I fix a set of bias values and I vary the parameters, I get that the revenue function is piecewise linear. Right? So what I really do, I use the structure of these dual functions that are parameterized by evaluation vectors v and takes as input parameters vector p, as a structure of this dual function to then give a bound on the pseudo-dimension of the original primal class of functions. Okay, so it's a novel proof technique from a learning theory point of view as well. So I find this very cool. Okay. All right. So this is actually a general result. Now let me give you a couple of examples from mechanism design. Okay, let me just check some other first. Okay, and so the first example that I'm going to talk about is posted prices, right? So the family of posted price mechanisms. So this is for multi-item, multi-buyer scenarios. So what we assume that the bidders or the customers come in a fixed arbitrary order. And what we're going to do, we'll set a price per item, and then the customers come in the given order and buy what they want at the current prices. Okay, and what I claim is that the pseudo-dimension of this family of mechanisms is up to log factors the number of items squared. Okay, and notice that this family of mechanisms is parameterized by the prices we set on the items, right? So this is what is parameterized by. Yes? What do you mean by this? Yeah, well, like in the sample complexity theorem that I had earlier, the uniform convergence bound depends on the upper bound on the values. So it's really like the deviation on the average, right? I said these uniform convergence bounds give you upper bounds on the deviation between the expected revenue overall and the revenue, the empirical revenue over the sample, average revenue over the sample, and the upper bound depends on, looks like h times square root of the dimension over n, or h is an upper bound on the value of valuation of on any given bundle. Right, so if that goes to infinity, then that uniform convergence bound is meaningless, right? So yeah, the bound will depend on that range, of course. Yeah, you can, in general, yeah, I mean, yeah, you can do Gaussian distribution over what? Oh, yeah, yeah, so you can use a specialized, Any
distribution sub-Gaussian should be fine.
Yeah, so the general sample complexity results depend on the value h, upper maximum, right, on the range, but of course there are specialized arguments that, and I think you had papers in the directions, and others, right, of course. If you make more assumptions, right, then you can handle also infinite, infinite ranges, yeah, with additional assumptions. 10 minutes, yeah, cool. Right, and so, right, what I'm doing here is, right, for this family of posted price mechanisms, what is going on again here? This has some problems. Oh, it's my computer. Right, so what I'm going to show here is that for this family of posted price mechanisms, the pseudo-dimension is up to log factors number of items squared, which then can be used to give this upper bound, to give uniform convergence bounds. And again, those bounds will include both the pseudo-dimension and in the most basic uniform convergence bounds, that value h that we're talking about. Okay, but what I'm going to focus is on showing how we can use our general theorem from the previous slide. Here, this theorem that gives us a bound on the pseudo-dimension of mechanisms that are dt delineable. I'm going to show you how we can use the theorem to prove this upper bound on the pseudo-dimension for these posted price mechanisms. Okay, so the first thing to notice is, so what we're going to show is that actually this family of mechanisms is dt delineable, where d is the number of items, so the number of parameters is the number of items, and t the number of hyperplanes that partition the parameter space such that within each partition the revenue function is linear, within each cell the function is linear. So we're going to show that t here is the number of hyperplanes is the number of bidders times 2 to the number of items choose 2. Okay, and once we're able to show that this family of mechanisms is dt delineable with these values of d and t, then we immediately get the bound on the pseudo-dimension by plugging into our general theorem. Okay, and again, by the way, this also, so we are not the first ones to prove bound on the pseudo-dimension of dt, on the pseudo-dimension of posted price mechanisms. Jamie and Tim had such bounds before, but again, much more involved arguments.
Question, is it really the number of items squared? Because naturally you would expect there are only n parameters, only number of item parameters, and that should be the pseudo-dimension. Is this like just an artifact of the method, or is this the right answer?
It's a great question. I love your question. One thing is I don't know exactly what's the answer here. Do you have a lower bound here for this one? Maybe not, but it is a great question. Not for this problem, I guess we don't really have an upper bound. But the interesting fact I can tell you that we've been looking at sample complexity of mechanism design and more general algorithm design. And because what we are now learning, so you're right. In general, in machine learning, especially when you have typical classes of functions to encounter, you'd think that there is like the number of the dimension is correlated to, it's typically connected to the number of parameters. Very natural, definitely. This is the kind of a very natural belief. Now, it turns out that in this algorithm design setting is not always the case. So we definitely have examples, for example, from clustering problems. We are trying to learn a clustering algorithm where you have one parameter, and the pseudo-dimension is probably lower bounded by log n, or in fact, even n. So that's cool because, and why does it happen? Is because now there is a more intricate relationship between the inputs and the outputs. The outputs are potentially combinatorial, and and these mechanisms have modules, right? And you can there is interdependence between these modules, and could definitely be in situations where slight changes to the input lead to drastic changes in the output. And because of this, now the pseudo-dimension is these mechanism families are much more complex, and so there is not always a relationship between the number of parameters and the pseudo-dimension. And in fact, the pseudo-dimension can be much higher than the number of parameters. Great question. But for this, actually, that's a nice open question. If we don't know the answer, yes, the question is for item pricing, what's a lower bound also on the pseudo-dimension? So yeah, I don't know if in this specific case it's an artifact of the proof or not, but we know that in general, once we look at there might not be a direct connection between the two quantities. Great. But so now, using our proof techniques, which in this specific case might be loose, let me tell you how do you use it. So it's actually very easy to prove it. So first of all, we're going to prove that this family of positive price mechanisms is DT delineable. So D here, the dimension of the parameter space is natural. It's just the number of items because we only set one price per item, right? So this is the number of parameters that we have, the number of items. And now what we're going to prove is that given if we fix a set of Bayer's values, we can partition the parameter space with this many hyperplanes, the number of Bayer's times 2 to the number of items choose 2, such that within each region induced by these hyperplanes, the revenue function is linear. Okay, this is what we're going to prove. And the quick overview of the proof is as follows. For every Bayer's and for every pair of bundles, if you think about it, the decision boundary where the buyer prefers one bundle over the other is a hyperplane. Yep. Okay? And so basically that means that because the number of bundles is 2 to the number of items, that means that we have the number of buyers times 2 to the number of items choose 2 hyperplanes, such that for any induced region in the parameter space by these hyperplanes, for any 2 prices in that region, any buyer has the same preference ordering over bundles. And now the key observation is that when all the buyers, the final key observation is that when all the buyers' preference orderings over all the bundles are fixed, the bundles that they end up buying are also fixed. So then within each region, the profit is a linear function of the price of the items that they buy. Okay, so it's kind of easy to show that basically for these positive price mechanisms, we can partition the parameter space with at most T hyperplanes, or T is this quantity here, such that within each region induced by these hyperplanes, the revenue function is linear. Okay, and again, by just using this fact, then we immediately get an upper one on the pseudo-dimension. Okay, that's one example. And I only have 5 minutes. I'm going to just quickly mention another example, and then I want to end up with some more general comments. So let me give you another very different example. So this is for 2-part tariffs. So here we have a single item, and we have a multi-buyer scenario, and we assume that we have multiple units of the item. If you want, you can assume an analytic number of copies, but we're going to assume that each buyer wants at most a limited number of units, or say at most kappa, calligraphic kappa units. Okay, and so what are these 2-part tariffs? I guess they come from economics. So if we have 1 2-part tariff, so the way it goes, the seller sets an upfront fee P0, and then a fee per unit P1. So if you buy anything, you have to pay at least P0, and then if you, an entry fee P0, and then additional fees per unit. So so if you buy K units, where K is at least it's at least 1, then you pay P0 plus K times P1. Okay, and then of course each buyer buys a number of units that maximizes utility, which is the value minus the price. Okay, this is one two-part tariff, but in general we can have a many of L two-part tariffs, and then in this scenario the buyer will choose a tariff and the number of units to buy that maximizes his own utility. Okay, and so now for this family of mechanisms we can prove it. So now if you have the class of length L menus of two-part tariffs, we can prove that the pseudo-dimension is up to log factor upper bounded by L, while L is the number of menus. So actually, in this specific example, there is a nice relation between the number of parameters and the pseudo-dimension. Okay, and the way you'd prove it, and I'm not going to go through the details, the way again to prove it is you're going to prove that this family of mechanisms is dt delineable, where d is 2 times L, this is the number of parameters, and t, the number of hyperplanes, will be this quantity, the number of buyers times L times kappa squared, where kappa is again an upper bound on the number of units that the buyer might buy. Okay, and you can easily prove it. I'm not going to go through the details, just like similar proof that I had before. Okay, but because I only have 2 minutes, I want to just mention that, right, so this proof technique, like where you show the mechanism class is dt delineable, it applies not only to the examples I mentioned, but applies to many other families of auctions. We show in our paper, like Affine maximizer auctions, restricted class of Affine maximizer auctions, you can again use the same proof technique. So once you have the right level of abstraction, you can easily prove pseudo-dimension bounds on many, many more mechanism classes. Okay? And so I think it's kind of cool because it's a simple proof that gives you many, many sample complexity results at once. Now, I think there are many cool, many interesting open questions here. So, okay, so, I guess again to summarize, basically what I just showed you is a general sample complexity theorem that applies to mechanism classes whose revenue function is a piecewise linear function of the class parameters. And this has already many applications, but the underlying methodology that I talked about should be even more broadly applicable to other mechanism design settings beyond selling, right, which is done here. Beyond revenue maximization should be applicable to your favorite mechanism design problem, data-driven mechanism design problem, and in fact should be applicable to even to just more generally to data-driven algorithm design. And in fact, there is a whole recent line of work that does exactly this. And we were part of it as well. The only, I want to mention one thing. So nobody asked me this question. When I give this specific talk, there is always a question that is asked. Okay, there is often a question that people ask is, well, right now you assume dt delineability, like you assume that you can partition the parameter space with hyperplanes, and inside is the part of the given inside each of the region given by the partition, the revenue function is linear. So in other words, I'm assuming that the revenue function is a piecewise linear function of the parameters. But what if it's not piecewise linear? Like, because probably you can put down mechanism design settings where they're not going to be piecewise linear. Can you still prove a sample complexity result? And the answer is yes. And actually, we're motivated to do this because when we started looking at other algorithm design problems, turns out, right, so for the function classes that I looked at today, like posted price mechanisms and second price auctions or reserves and two-part tariffs, the revenue function is indeed piecewise linear. But when we started looking at other families of mechanisms, of algorithms from other settings, the revenue function is, or the corresponding functions are not piecewise linear anymore. And so I'm going to skip quickly through this. All I want to show to you is actually a cool picture. So it turns out you can prove a general sample complexity result that applies to cases where if you fix an input of the problem, instance of the problem, and you vary the parameters, you don't necessarily get a piecewise linear structure, but you get a more general structure. So here is the assumption that I have a picture, nice picture here. So what we show that if we fix an instance of the problem and you vary the parameters of the underlying family of algorithms, we imagine that we can partition the parameter space with some functions coming from a function class f. So these are the boundary functions, such that within each part given by this partition, within each piece given by this partition, the corresponding cost function is nice, comes from a function class g. Right, so if I'm assuming that these kind of dual functions are piecewise structured in this way, then I can give a bound on the pseudo-dimension of the family of algorithms that I care about. Right, and in our auctions case, the boundary functions, and the theorem that I presented to you from the EC 18 paper, the boundary functions were linear, and inside each piece, these functions are also linear functions, but in general they can be much more complex. They can be any quadratic boundary functions and so on. They can be, really in general, they can be, these boundary functions can come from a function class f, abstract Mechansim function f, and the functions within each piece can come from a function class G. And when you can keep bounds on the pseudo-dimension, the original function class we really care about is a function of the niceness of its boundary functions and of these functions inside this piece. Okay, and this is much more general, and I would conjecture to apply to any mechanism design problem you might sit down to think about. So I think it would be really cool if for some of the problems that you are working on, somebody was mentioning social choice over dinner and so on, if you can use this general theorem to solve some data-driven mechanism design for the problems you care about. Great, so I'm going to stop here.
We have time for questions, please.
I have a question.
Yeah.
So, can you exploit any structure in the underlying distributions to improve your bounds?
Yeah, so that's a great question. So right now, the answer will be in general yes. Yeah, because right now we prove bounds on the pseudo-dimension. If you want to prove this uniform convergence, very general bounds, we're going to be on the pseudo-dimension. So if it then you cannot make additional distribution of the underlying distribution. But if you go to Rademacher complexity bounds, then you can exploit the structure. So this will be data-dependent bounds. So the answer is yes, but you'd have to look at a different measure of complexity, Rademacher complexity. And I think we've done some of it for some of the examples, right? I mean, so in the paper we have many examples, right? So do you remember one of them? So that's the advantage of having Ellen in the room.
Yeah, for some of these like simple classes, like second-price option with reserve for multiple items, or like posted price mechanisms, when the buyer's values are independent, we have some bounds for that.
Improved bounds over the pseudo-dimension bounds, right? You can go and compute the Rademacher complexity, and
And you lose like the dependence on the number of bidders, I think, if I remember.
Okay, but you still need to know something about the auction class, right?
Yeah.
yeah, you will still need to assume something about the auction classes being parameterized and being of a specific form. But if you make additional assumptions about the underlying distribution, you can use Rademacher complexity bounds to get tighter bounds than these bounds based on the pseudo-dimension.